I'm Kaz Sato. I'm a developer advocate for Google Cloud Platform, and I'm also a tech lead for the data and analytics team. I have been working at Google for over 5 years, and for the last one and a half years, I have been working as a developer advocate to having presentations like this at many events. So in these sessions, I'd like to talk about these agendas. But first, I'd like to introduce the concept of neural network and deep learning and how it works with very great demonstrations. And also, I'd like to introduce how Google has been deploying those neural network technologies to the Google Cloud. And then I'll be covering the technologies and products that those are actually provided as products from Google Cloud platforms. So what is neural network? So neural network is a function that can learn from training data sets. So if you want to have neural networks to do image recognition, then you can put for example, cat images converted into a large vector, and then put that vector into the networks. Then eventually, you would have another output vector which represents the labels of the objects detected, such as cat or human face. So it's designed to mimic the behavior of neurons inside human brains by using matrix operations. So actually, it does very basic matrix operations only. There's no sophisticated or fancy mathematics going on. Everything you do with neural networks is you have the matrix operations you have learned at high school. For example, the input vector may represent the image of cat. Then you would have a vector that would have the pixel data converted into a vector. And you would get another output vector as a result. That represents the label of the detected images. In this case, you would have any number closer to the 1.0. That indicates the neural network thinks the image must be a cat. But the things going on inside the neural networks is very simple. All you are doing with neural network is the matrix operations, like wx plus b equals y, where the w's are weights and b are biases. And actually, you don't have to care about those w's and b's at all. You let computers find and calculate the w's and b's. So all you have to care is what kind of data you would want to put into the networks and what kind of the result you want to get. So let's take a look at some interesting demonstration of neural networks. For example, if you have a problem like this, the very simple classifications, how you can use neural networks to do the classifications of these two different data sets. I'm not sure what those data points means, but let's imagine that those are the data of the weights and height of people, so that if a person's weight and height are both low, then you can think he or she must be a child, or maybe he or she could be an adult. How can you classify them? If if you try to use neural networks to do this problem, then you can just apply the same equation, wx plus b equal y, to do the classifications. So you are putting the weight number and height number here as a vector, and you will get an output vector like this, where if one single data point isn't classified as an adult, then you would have one here. And if it's a child, then you would have one here. And thing is that computer tries to find the optimal combination of the parameters, such as the weights and biases, by itself. And you don't have to think about what kind of the parameters you have to set to neural networks. Computer does it for you. So let's take a look at the actual demonstration. Did you see that? So I can do that. Okay. So instead of the humans letting computer instructing, learning, you don't have to teach computers how to solve these problems. Everything you have to do is provide the training data set so that computer thinks by itself to optimize the combination of the parameters such as weights and biases. So you see that the computer is trying to change the weights to do the classifications at optimal success rate. And now computer is using an algorithm called gradient descent. That means it tries to increase or decrease each weights and biases to make the combinations closer to the higher accuracy or lower loss rate. So it's just like the learning things from the parents or the maybe senior people in your company, where these junior people or the children are learning from many mistakes. So computer makes many mistakes in initial stage, but if you provide much more training data set, then computer using the gradient descent algorithms try to minimize the failures. So that's how it works. So let's take a look at another interesting demonstrations of neural networks, where we have another training data sets like this. I'm not sure what does it mean, but let's think that we have some data sets which requires complex classifications. If you are programmers, maybe with this data set, you may want to use maybe equations for circle to classify the two data sets, blue data sets and orange data sets. But by using neural networks, you can just let computer think how to solve it. Now you saw the computer was trying to create a pattern to classify those data sets by using so-called neurons in the hidden layers. With the first example, we didn't have any hidden layers. But with this complex data set, you need to use the hidden layers. That means between the input data and the output neurons, you would have another layers between them that has multiple neurons. And each neuron does very simple things. These neurons only classifies whether the data point is in the bottom left area or the upper right area or not. These neurons only classifies whether the data point is in the left or right, just like that. But combining those outputs at the last neural network, then the neural networks can compose much more complex pattern like this. And if you have more and more neurons inside the hidden layers, then the network specifications, speculations can be much more accurate, like this. So by adding more hidden layers with more neurons, you have to spend much more computation power, but at the same time, the neural networks can compose much more complex patterns and extract the patterns from the large data sets. How about this? Let's try it. This is a data pattern called double spiral. If you are a programmer and your director or customer asked you to classify this kind of data set, what kind of program code you would write? Do you want to write many if statements or switch statements with many thresholds? Try checking the X and Y positions? No, I don't want to do that. Instead, I would be using neural networks. So that neural networks try to looking at the data points in the data sets to find the optimal patterns hidden inside the training data set. Just like this. So this is where the neural networks can exceed the human performance, human programmers' performance. It can extract those hidden patterns inside the training data set. And you don't have to specify anything. They call it features. You don't have to do any actual features by human hand. Instead, computers can find the patterns from the training data set. So that's why people are so excited with the neural networks and deep learning. How about this? So if you have the problems of the identifying the handwriting text, you can still using the very simple the W express B equals Y kind of neural networks to classifying this handwriting text. The networks would come up with these complex patterns that can classify those images into the vectors with the labels like 8 or 7 or 6. And if you want more accuracy, then you would have more and more hidden layers so that you could get like a 85 or 95 or 98 accuracy. And how about this? How can you classify these cat images by using neural networks? You have to have many more layers of neural networks. That is so-called deep neural networks. This is a diagram called Inception Model version 3 that has been published by Google last year, where we have used 40 hidden layers in a single neural network design. So it takes much more computation power and time, but still it can learn much more complex compositions like this. The neurons closer to the input vector could learn very simple pattern like this, like vertical lines or the horizontal lines. But the neurons closer to the output vector could learn much more complex patterns or compositions such as eyes, nose, or human face. Again, we didn't put any features or patterns embedded in the neural networks before training it. So everything can be trained from the data set by using computation power. So that's how neural network and deep learning works. But as I mentioned, it takes so much computation time and training data sets to use deep learning for the production projects. So there are two big challenges right now for the users for the deep learning. And this is why deep learning has not been so popular for you guys. Once we have solved these problems, like if you have plenty of computation power with a plenty training data set, then you can easily apply neural networks or deep learning to your existing problems. If you're a game programmer, you may want to apply the deep learning to analyzing your game logs, server logs, to check whether a player could be a cheating player or spammer or something like that. Or if you're web designer or web systems engineer for the ads system, then you may want to apply the logs for the ads conversion or click-through rate logs to neural networks, so that you can have computers to learn from the ads log to get more optimization. But you have to have computation power and training data. So that's the reason why we have started using Google Cloud to train the large-scale neural network. Google Cloud has hundreds of thousands of machines in our data centers in global, and we have been building those computers as a data center as a computer, not just a bunch of the computers we are building. We design each cluster, which holds like 10 or 20,000 servers, working as a single computer with multiple CPUs. So that's the reason why we can. It's not so hard for us to deploy large-scale neural networks or large-scale big data processing to our Google Cloud. There are two basic, very fundamental technologies inside Google that supports the data center as a computer. One is the network. We have been building our own hardware for the network switch fabric. That is called Jupyter Networks. So we are not using the commercial network switches for most cases, such as the Cisco or the Juniper routers. Those are not mainstream of our network backbones. We have been building our own hardware that can hold like 100,000 ports of 10 gigabit Ethernet ports that can yield 1.2 petabit per second per data center. So that is the networks we have at Google. And also container technology called Borg. Borg is our proprietary container technologies we have been using over 10 years for for deploying almost all Google services such as Google Search or Gmail or Google Maps. Bulk containers can hold up to 10,000 or 20,000 physical servers in a single cluster, so that you can do the large-scale job scheduling, like the scheduling the CPU cycles or memory spaces or disk IOs with that scale. So that's the reason why you can deploy your single applications, like the neural network training or the big data processing, into maybe hundreds or thousands of machines with a single line of the bulk command. And Google Brain is the project where we have started applying the Google Cloud technology to build the large-scale neural networks. This project has started in 2011. And right now, the Google Brain has been used for the many production projects in Google. And what's the scalability of Google Brain project? For example, RankBrain. RankBrain is an algorithms we are using for the ranking of Google search service right now since last year. That has been using Google Brain infrastructure and with 500 nodes, and that can perform at 300 times faster than single node. So that means if you are training your deep learning model with single servers, then you would take 300 times longer than Google's engineers. And Inception is the model for the vision recognition. We can use 50 GPUs to accelerate the performance at 40 times faster. So that's the reason, those are the reasons why Google has been so strong on applying deep learning for the production projects, such as the AlphaGo, where we have the series of the Go matches with the Go professional. They have been using the Google Brain infrastructure for the training as well as the prediction of the Google match. Google Search has been using the Google Brain since last year, and we have been using the machine learning technologies for the optimizing the data center operation. And also OCR, natural language processing, and visual recognition or speech recognition, such as the Google Photos or the voice recognitions of the Androids. We have over 60 production projects that has been using Google Brain and deep learning for the last couple of years. Now we have started to externalizing this power of the Google Brain to external developers. The first product is called Cloud Vision API, and the second product is called Cloud Speech API. Cloud Vision API is an image analysis API that provides the pre-trained model, so you don't have to train your own neural network. And you also don't have to have any skill set for the machine learning. So it's just an REST API. You can just upload your photo image to API, then you'll be receiving JSON result in a few seconds that has the analysis result. And it's free to start trying out up to 1,000 images per month. And it's generally available right now, so it's ready to be used for the production project. It has 6 different features to be detected. Label detections means that you can put any labels or category on any images you uploaded. For example, if you're uploading the cat images, then the API will be returning the labels such as a cat or pet. Face detections can detect the location of face in an image. OCR can convert the text on the image to a string. Explicit content detection means that you can check whether the images can contain the adult or violent images or not. Landmark detection can detect the location of the images of popular places, and you can also detect the product or corporate logo. Let's take a look at the demonstration. So I'd like to show a demonstration by video at first. This is the demonstrations by using the Raspberry Pi robot that sends the image to the Vision API.
Cloud Vision provides powerful image analytics capabilities as easy-to-use APIs. It enables application developers to build the next generation of applications that can see and understand the content within the images. The service is built on powerful computer vision models that power several different Google services. The service enables developers to detect a broad set of entities within an image, from everyday objects to faces and product logos. The service is so easy to use. As one example of the use cases, you can have any Raspberry Pi robot like GoPiGo calling the Cloud Vision API directly. So the bot can send the images taken by its camera to the cloud and can get the analysis result in real time. It detects faces in the image along with the associated emotions. The Cloud Vision API is also able to detect entities within the image. Now, let's see how facial detection works. Cloud Vision detects faces on the picture and returns the positions of eyes, nose, and mouth. So, you can program the bot to follow the face. It also detects emotions such as joy, anger, surprise, and sorrow. So the bot can move towards smiley faces or avoid anger or surprised face. One of the very interesting features of Cloud Vision API is the entity detection. That means it detects any objects you like. Let's see how it works.
It's glasses. It's banana. It's automobile. It's money.
You see? Cloud Vision lets developers to take advantage of Google's latest machine learning technologies quite easily. Please go to cloud.google.com/vision to learn more.
Okay, and I have another interesting demonstration that is made by using the Vision API. This is called Vision Explorer demonstrations, where we have imported 80,000 images downloaded from Wikimedia Commons and uploaded to the Google Cloud storage and applied the Vision API analysis. So here we have the cluster of the images, 80,000 images. And each cluster has the labels such as snow or transport, residential area. Means that there's a cluster of the similar images. For example, if you take a look at let's go to the plant. So each single dot represents the thumbnail of the uploaded images. So if you go to the plant cluster, there must be some cluster of the, it's not showing. Why? Let me reload this. Maybe because I'm using tethering. Okay, let's go directly to the cat cluster. So in this cluster, we have many cats. And closer to the cat cluster, we have the cluster for dogs. And let's go back to the cat cluster. And if you click to image thumbnail image, then you'll be seeing the analysis result from the API like this. The API thinks this must be an image of a cat, and it's a cat as a pet, or it must be a British short hair. So this is something you can do with the deep learning technology. And those results are returned in a JSON format like this, and with these demonstrations, we can show it in a GUI. If image contains any text inside it, then we can convert it into the string. For example, with this, you can have the string like this: 3 kangaroos crossing the next 2 kilometers. If images contains faces, although this API doesn't support any personal identification or the personal recognition, but it can detect the location of the faces with landmark locations such as nose and mouth. And also it can recognize the emotions such as joy, sorrow, and anger, and surprise in this confidence level. And if your picture contains any popular places such as this, then API can return the name of the landmark. The API thinks it must be an image of the Citi Field Stadium in New York City with the longitude and latitude. So you can easily put a marker on the Google Maps. It's too slow, so I'm cutting it down. Also, you can detect the product and corporate logo, like this Android. So this was this Vision API, so it's ready to be used for any applications. And another API is called Speech API, which also provides the pre-trained model for the voice recognition. So you don't have to have any skill set or experiments with the voice recognition or training neural networks for doing that. It's just a REST API and gRPC API. So you can just upload your audio data to the API, and you'll be receiving the result in a few seconds. It supports over 80 languages and dialects. It supports both real-time recognition and batch recognition. The API is still in the limited preview, so if you go to the /speech cloud.google.com/speech, then you have to sign up with a form for limited preview access. But we hope to make it public beta, maybe in a couple of weeks, I suppose. Let's show some demonstration. I'm not sure if this works in the event or not, because this is the first time to try this. And I have some accent problems, so I'm really not sure if this works or not, but let's try. Hello, this is a testing of, I think it's not working. Maybe the tethering is getting so slow. Hello, this is a test of voice recognition by Google Cloud Machine Learning. Oh, yeah. So final result is, not bad, right? And you also saw the fast response. So you could get the recognition result in less than 1 second. It's like a 0.5 seconds in real time. So those are the APIs, but those APIs here are pre-trained model. So that means you cannot train your own model with those APIs. And one of the frequently asked questions for those APIs is that whether the Google will be looking at the uploaded images or the audio data to train your own model or doing some more research. And answer is no. Those APIs or all of our products are provided by the Google Cloud Platform is under the terms and conditions of GCP. That has some sections for the customer data. We don't look at the customer data except for the very special cases for the troubleshooting or emergency situation. So basically, we don't look at your data uploaded to the cloud. But at the same time, so the APIs cannot do the trainings for your data or your applications. So that's the reason why we provide the other options for machine learning as TensorFlow or cloud machine learning. Those are the frameworks and the platforms that can use for train your own data set, train your own machine learning and neural network. What is TensorFlow? TensorFlow is an open source library for machine intelligence. We have published the libraries last November, and this is the actual framework we are right now using at the Google Research or Google Brain team. So it's not something outdated or stale. It's the latest machine learning framework we are using right now at Google. For example, if you want to design the simplest neural networks like the WX plus B equal Y, you can use Python to write it in a single line of code like this. You can put the image of a cat here with vector, and then you would have an output vector that represents the labels of the detected objects like a cat or human face. And you can let computers to find the weights and biases. So it's so simple. And also, it's really simple to train your networks because you can just write this single line to have neural networks trained for your training data set. By specifying the algorithms like a gradient descent, you don't have to implement your own the procedural code to implement the optimization logic. Actually, I'm not good at math or those machine learning algorithms, but still, I can just copy and paste the sample code to my laptop and playing with my own data sets with TensorFlow. So you can just let the TensorFlow runtimes to do the optimization. And also, the tool provides a very good visualization tool. So one of the problems we had at Google for applying the neural networks to the production problem is the debugging. So if you have many more hidden layers inside the neural networks, you have to check all the status of the parameters, whether the parameters are converging in the right direction, or the parameters could be, going away and having a wrong number, such as a NAA or 0, something like that. So it's really important to visualize what's happening inside the neural networks, and TensorFlow provides the tool. And also, the portability is another important aspect of the framework. So once you have defined your neural networks with Python code of TensorFlow, then you can start running your neural network training or prediction with your laptop, like a Mac or Windows laptop. But you will find that your laptop is too slow to train the deeper neural networks. So maybe you may soon want to buy some GPU cards and insert maybe 2 or 3 GPU cards in a single box. But still, usually it takes like a few days. Usually it's a few days, or maybe some people spend a few weeks to do the trainings on their neural networks. So it takes so much computation time. So in that case, you can upload your TensorFlow graph to Google Cloud so that you can utilize the power of the tens or maybe hundreds of GPU instances we are running at Google Cloud. And also, once you have finished your training, then the size of the parameter sets could be fit into like hundreds of megabytes or tens of megabytes. Then you can easily copy that parameter sets into the smaller devices, mobile devices, or IoT devices such as Android, iOS, or maybe Raspberry Pi, so that you can have those devices doing the prediction, like image recognition or voice recognition, without using any internet connection. Everything could be done, implemented within the framework of TensorFlow. And with at the last Google I/O, it was about 1 month ago, we have announced a new technology called Tensor Processing Unit. This is a replacement, not a replacement, maybe a complementary technology for the GPU and CPU. So far, or maybe right now, any neural network researchers or developers outside Google is using GPUs mostly for training the neural networks because it's a matrix operations. And by using GPUs, you can accelerate the matrix operations 10 times or maybe 40 times faster. So that's what typical neural networks users are doing right now. But the largest problem for GPU is the power consumption. It consumes like 100 watts or 200 watts per GPU card. And we are using thousands of them in a Google data center. And power consumption is becoming the largest problem. So by designing the ASICs or the LSI chip specifically for the TensorFlow or deep neural networks, we were able to reduce the power consumption and gain the 10 times better performance per watt result. And we also use the special techniques such as the bit quantization. Rather than using 32-bit or 16-bit to calculate everything, every matrix operations, we use the quantizations, like a quantizer into the 8-bit, where there's not so much loss of the accuracy, so that you can fit much bigger parameter sets into a very small memory footprint. And we have been using the TPUs for many production projects already. RankBrain, AlphaGo, and Google Photos, and speech recognitions. These are all has been using TPUs since a couple of months. Actually, we have been using TPUs for last 1 year. And if you want to, I have been describing about the power of the Google Brain, such as the number of the CPUs, GPUs, and TPUs. And if you want to utilize the power of those Google Brain infrastructure, here's the product we provide, which is called Cloud Machine Learning. Cloud Machine Learning is a fully managed distributed training environment for your TensorFlow graph. So once you have wrote your TensorFlow graph and run it on your laptop, then you can upload the same TensorFlow graph to Google Cloud Machine Learning, so that you can specify the number of the GPUs you want to use with the service, such as the 20 nodes or 50 nodes, to do the acceleration on the training. Right now, Cloud ML is in the limited preview, so you have to sign up to start trying out. But maybe we suppose that the full availability, like a public beta, will be sometimes later in this year. If you go to the YouTube, then you can take a look at the actual demonstration of Cloud ML by Jeff Deans, where he has demonstrated the actual TensorFlow-based neural networks that takes 8 hours with single node. But if you upload the same TensorFlow graph to the Cloud ML, then you can accelerate the performance to up to 15 times faster. That means you could get the result of trainings within 30 minutes rather than waiting for the 8 hours. That is the speed we are seeing inside Google for any deep learning deployment. And we are externalizing this power to you guys to have you utilize the power for solving your own problems. And also, Cloud ML can be used for the prediction as well, not only for the training. And in the demonstrations he demonstrated that the Cloud ML could be used for the predictions at 300 requests per second. So those are the topics I have covered. And now we have two different products. One is the ML APIs, like a vision API or speech API, where you can just upload your own data to cloud so that you'll be getting the results in a few seconds. And if you want to train your own neural networks, then you can try using the TensorFlow or Cloud Machine Learning so that you can accelerate training your own neural network. So if you take a look at the links and the resources of these slides, then you can start trying out those products right now. Thank you so much.
I got two questions through the app. First of all, a few steps back on machine learning and neural networks. Mm-hmm. You told about the more hidden layers, the more complex the algorithm. Yeah. But is there a max for it? Or is there, like we were taught in university, to use your feeling to see how many layers? Do you have any tips on that, or?
Yeah, that's actually a really good question. So maybe question is there any good practice on designing your neural networks, right? So as far as I know, there's no theory to optimize your design of neural networks. So everybody, even inside Google, when I ask the Google research team, and people would say, let's start with the five hidden layers and let's see how it works or something like that. And that's the largest challenge we have right now for deploying the neural networks for your own data or applications. So you have to do the many trials, just like the people in the pharmaceutical companies trying to create a new drug. So you have to have the different combination of the hyperparameters. Hyperparameters means the parameters such as the number of the hidden layers or neurons, or the way you can import the data or extracting features. So you have to try out every different combination. That's the problem. And also it takes much computation power.
Yeah, I think that's what all do.
Yeah.
It's not a theory behind it. And a little bit later in the presentation, what use cases will be supported in the near future for going from post-training to runtime? Can networks V and B be exported in order to use an embedded processing, for example?
What's the second question?
Can the networks V and B be exported in order to reuse in embedded processing, for example?
Exporting.
Yeah.
Okay, yeah. For the first question, which is the online training, I think it's on the roadmap or maybe the list of the requests, but currently it's not supported. But it's possible that we will be supporting the online training where your neural networks will be gradually trained by the online data. And second question is exporting. Yes, you can export the trained parameter sets so that you can use the parameter sets to your any use cases, such as the importing the parameters into the IoT devices, or maybe you can even copy that data sets into different cloud like AWS to learn your predictions on AWS.
Okay, those questions I got. Do anyone else has any questions? No? And thank you very much.
Thank you so much.